Okay, so let us start the class. So, hello, I am Rajiv. I'm the TA for this introductory field structural geology course, and I am here to take the live session. And this is the second class, second live session. In the previous week, we talked about the week one course materials that are mostly how to orient yourself in the field and what are the tools and instruments we generally use to map the different structures and their geometric disposition around the space. And also, we talked about the use of planar and linear data to uh, interpret their structural relation, and for that we have also talked about the basic concepts of stereo net and or stereographic projection and how do we use them to calculate the strike, dip, pitch, plunge, trend, etc., planar and linear data, and how the basic concepts of how we plot a plane, a pole, a line, etc. So in this live session, that is the second live session of this course, we will talk about the course materials, the lectures for week 2, and we will have some specific discussions about the different kind of primary and secondary structures we generally see in the field, and there are some concepts we would like to basically discuss those things. So without further ado, let me share my screen and then we will dive into the different concepts. Okay, so is my screen visible? Okay, so so in this live session we will discuss few points, right? So the first is, so this is the live session for week 2. In this week we have been taught about primary structures, which includes bedding plane and most importantly uh, the current ripples and seen sedimentary deformations, right? And in the second part of this week we also talked about the secondary structures, which includes the foliations and lineations, different kinds of lineation. Okay, and we also talked about the importance, regional importance of these different kinds of structures and how we utilize them to understand the regional tectonics of a particular area, right? So in this regard we will be discussing about 4 different topics. So topics of today's discussion: So number one is how to determine or how to differentiate between thin sedimentary deformation and tectonic deformation, right? So this is a most important part that we generally observe in the field, is that there are a lot of structures. There can be tectonic deformations, there can be thin sedimentary deformation, but everything has to be from different origin, right? But in field, how do we exactly interpret or rather differentiate that? Okay, so this is thin sedimentary deformation and this is a tectonic deformation. We have to be sanguine about that. So how to differentiate between thin sedimentary deformation and tectonic deformation in field, right? By looking into the structures, right? And then we will discuss the formation as well as the evolution of simple to complex thin sedimentary structures, right? And these thin sedimentary structures have different utilities. So coming to utilities, one is of course determining the stratigraphic yonging direction, and the other one is of course use of these structures as strain markers, right? So this is the second agenda of this discussion. Now the third point I believe is very important in field is to estimate a planar geometry from uh, secondary linear data and statistical estimation. I mean statistical significance of data. This is very important. Okay, that means statistical significance in the sense I am trying to talk about how much data should we collect and how much data set would tell us that okay, so this is a robust measure and there is a little amount of error within that data, right? Okay, and the fourth one is of course the relationship between planar and linear fabric. And in this regard, it is very important to identify how do we interpret the large scale, I mean regional scale s- structure, even though there are no direct evidence, right? So these are the discussions, topic of discussion we would like to go on today specifically. So let us start with the first thing, which is the differentiation between the primary and, I mean, sin sedimentary deformation and tectonic deformation. So the first point, right? So I assume that you all have gone through the different lectures in this week. Precisely, it was in the first two lectures that we observe how we see different kind of sin sedimentary structures, like say for example current ripple, overturned ripple, convolutes, right? These are the main structures that we have observed in the field, specifically in the Ghatshila region, the Fairy Ghat and the Chitradurga, sorry, Harindungri village and the abandoned airport, these kind of sites. I assume that you all have gone through those videos. Now, let us have a discussion about this. So, say for example, I am drawing a hypothetical structure. Say this is an outcrop, and you see these kind of things, right? I tell you, this is a sedimentary deposit. Not essentially sedimentary. Let us say that this is a metasedimentary rock. So this is a metasedimentary rock, right? So first of all, tell me, anyone, what is this structure? Any idea?
Overturned cross-bedding.
Okay, so the answer that we have got is overturned cross-bedding. And it is quite correct because in the video we precisely have seen these kind of structures, right, in the field. Now the question is, if I argue that no, this is not a overturned cross-bedding and this is a fold, then how would you differentiate between the fold and an overturned cross-bedding? It simply can be a fold, right? And I can argue that no, this is not a overturned cross-bedding. Just because you have seen it in the video, that doesn't mean that everywhere you go you mark these structures as overturned cross-bedding, right? Because then we have to make sense of our logic. Okay, so how am I differentiating this structure to be an overturned cross-bedding and it is not a fold? Then again have a discussion about it. So why do you think that this is precisely an overturned cross-bedding and not a fold? So I can say that counter argument. This is a fold, right? What should be the answer? What do you think? Any guess? Anyone? Anything can just say, because we are all here to learn, and therefore a healthy discussion should, I mean, increase both of our knowledge. I mean, I could also find some arguments that can have me thinking that okay, right, this can be even possible. So what do you think? Any idea? No one? So which courses are you in? I mean, anyone, are you, are you guys in masters or you're undergraduate, or anyone doing PhD, or just for your knowledge enrichment you have enrolled to this course? It's good to have a feedback that whom am I talking to, whether this is a batch of undergrads or masters. Anyone?
Sir, undergraduate.
Okay, so and your name is?
Sir, Jeevanandam.
Okay, where are you from?
Sir, Trichy, sir. National
uh,
College.
okay, 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 very good.
Thank you.
And so Jivanand, what do you think that what can be the answer is
Sir, overtuned fold means the anticline should be inclined. Generally, fold means
there is some issue with your mic, I think.
sir,
I mean, the sound is breaking. Uh, can you
sir,
hear
just
me? Yeah, I can hear you. Yeah.
overtuned fold means the anticline should be inclined.
No, no. Just not think about overturn fold, right? It can be any kind of fold, right? My argument is that why is it precisely a cross bedding and not a fold? Because I guess that you understand the difference between a cross bedding and a fold, right?
Yes, sir.
Because fold is formed precisely because of tectonic deformation. So it is a tectonic signature. And since sedimentary structures are not tectonic deformation, they are occasional uh, response to tremor or shaking that has produced, or any kind of disturbance. The disturbance
Okay.
can be tectonic disturbance, or it can be even some other causes. Say for example, uh, say in a lake or a pool. So here the sediments are depositing, right? So let's talk about some Jurassic period, and there is a lake and the sediments are depositing inside that lake. Now there is a steady deposition of sediments, but let us assume that a brontosaurus, that means these large herbivore dinosaurs. So these are heavy dinosaurs. They might have been passing from that beside that lake, and because of their heavyweight foot, I mean walking, it may have produced some shaking on the ground, and that is why the sediment deposition got disturbed, and eventually it formed a tiny little sin sedimentary deformation structure. So these sediment depositions, they are this kind of sensitive. Even there is a slight disturbance or shaking in the ground, whether it can be an earthquake, whether it can be something, some animal disturbance, any kind of disturbance can produce this kind of I mean this sin sedimentary structures. But folds are essentially related to deformation. So when we deform a rock, then only we can create a fold. So precisely, folds and crossbeddings, they are not similar. They are fundamentally different because of their origin, right? Now in this case, we don't know exactly, right? We are seeing a structure, and by the geometrical similarity we are assuming that, okay, so this either can be an overturned crossbedding or it can be a fold. Now my question is, in the field, how do you differentiate, right? Because if you interpret the structure wrongly, then your entire interpretation about the tectonics or the regional deformation of the area would be wrong. So these very fine judgments is required in the field that can give you a correct approach towards your tectonic studies, right? So think again that, why am I telling that these kind of sin sedimentary structures are not related to tectonics, and therefore there must be a way through which we can differentiate. So if you cannot just think at the moment, then I'm going to tell the answer. Before that, anyone other than Jivanand can would like to try? Anyone? Okay, so let us go back to our discussion. So let us see how these structures are forming. So I am making a column here. Sorry. Okay, so this is my sin sedimentary structure, and this is my tectonic structure. Now, how do these structures form? So imagine this is a water layer, not with black. Of course, water is not black. So consider this as a water layer. And then we have sediments, right, at the bottom. we have some sediment deposit. So these are layers of sediments, right? Sediment always deposits as horizontal layers. Now, if I zoom into this area, we see that within these layers, because of the tremor or any kind of disturbance, has created these convolutes. Suppose, say, example like this, right? Or say, for example, it has formed some overturned cross bedding. Now, these structures, since they are formed because of an instantaneous event, so it is very important to understand that instantaneous event, right? So instantaneous event or instantaneous disturbances, they are short duration events. These are short duration event, right? That means if an earthquake occurs, so can anyone say that what is the general duration of an earthquake? Anyone? What could be the maximum duration of an earthquake? Or let's say an average duration of an earthquake? Anyone? Jivanand, any idea?
Sir, minutes or few minutes.
Exactly. So the scale is within minutes, right? Within seconds to minutes. So because of this very short duration, the disturbance created because of this external tremor or earthquake or shaking should only restrict itself into some few layers, right? Because say for example the sediment, say for example this one, in this layer, while the layer was depositing, there was no event. So the sediments, they all deposited horizontally perfectly flat without any kind of disturbance. Same goes for this one, same goes for this one. But when coming to this fourth layer, we saw that there was a disturbance. So because this time of deposition is much greater than the time of this event, then because of that short instantaneous event, these structures would form locally and they would be restricted within few layers only, right? And then again, after that event, while the other layers were forming, say for example this one, there was no tremor, then there was a perfect sediment deposition, and even for the top one. So the main point is that duration of sediment deposition is much larger than the duration of external disturbance, right? Because of that, the formation of thin sedimentary structures are only restricted to few layers of the sediments locally. This is very important. These are not seen regionally altogether in all layers, right? So they are local phenomena. We don't even see these kind of structures all over the places continuously, right? So even though I think that you should also remember that while the instructor was showing the overturned cross bedding in the field, there were or there was precisely only one cross overturned cross bedding and not many more. You should have observed this, right? There was only one. That means, or that tells us, that these structures are local occurrences. They do not occur all over the places continuously. They are small scale structures and they occur in local places, not everywhere altogether, right? So this is the primary distinction that we can make out from this observation, that these thin sedimentary structures, since they're formed because of short duration external disturbances, they form locally and they are constricted within few layers only. So this is a highlighting point, and also this is a highlighting point. So thin sedimentary structures are local, restricted within few layers, and they are discontinuous. Okay, I hope you have understood this thing, that why it is discontinuous, local and restricted to few layers only. Now coming to the tectonic structures. Tectonic structures essentially form after lithification. Majorly seen to form after lithification. That is the primary reason for observing the deformed structures only in uh, metamorphic rocks, right? Observing majority of the structures. There are some examples where uh, the host rock, which is not metamorphosed yet, can show some signatures of deformation. Like in granite, we see that even in granite we can also observe small microscale shear bands or shear localization, shear deformation events, even though the entire granite hasn't gone undergone any kind of metamorphism. So tectonic structures are majorly seen to form after lithification. That is the primary reason for observing majority of the structures in metamorphic rocks. Okay. Then how these structures have formed? Now see, there are layers of rocks, right? Now the question is it possible to deform a single layer? Say for example, you have some layered sedimentary rocks, say sandstone, shale, sandstone, or mudstone, shale, mudstone, limestone. These kind of altered layers are there. So do you think is it possible for the tectonic forces to deform only a single layer and not all layers together? Think about it and say whether it is possible or not. What do you think? Anyone? Jivanan?
Sir, no, sir.
Why do you think it is it not possible?
Sir, the atomic structure between these sediments will be changed. So
Okay.
I think so.
Yeah, that is correct. But think about it. Think of it like an example is that, so you have a stack of papers and consider individual papers being different layers, right? So you have a stack of paper, right? I can give you an example, like I have this notepad here. So there are different, you can see there are several papers, right? Now the tectonic forces are not like, so if I am able to put a force only on the single paper, see, I can fold it, right? It is possible when I apply the force here over this end of this paper, then I can fold the layer, I mean fold the paper. But now if I am trying to fold like this, what is happening? So I am applying the stress all over this notepad, not on a single paper. What is happening? The entire layer of papers, or the entire stack of papers, is being folded. Now think about the scale of these tectonic forces. These are plate scale forces, right? Thousands of kilometers spread, these plates, and they are colliding with each other, and because of that the tectonic forces are being generated. So in that case, is it possible to localize the force only to one layer? I think it is not. And you can never localize the force or the entire tectonic force into one layer. That is not possible, because this is a large scale event. And even for a large scale event like a tectonic tectonic collision or like that, you cannot actually precisely localize this stress onto a single layer, which we are possibly seeing in the outcrop. And since we are talking about outcrop scale, then it is possibly in the scales from centimeters to meters. Whereas while comparing the entire uh, tectonic structure, we are talking about thousands and millions of kilometers. So from that perspective, this single layer is just like an atom in comparison to, uh, say for example, a human body, right? So that kind of scale differences take place. So it is never possible to deform single layer through tectonic forces. So as a result, what would happen? So of course this answer is no, at least with the tectonic forces it is not possible. Then what happens? The entire layers, all the layers are folded, they're buckled. Entire set of layers has to fold, right? Then if the entire set of layer has to fold, do you think that these structures or this folded sequence would be local and restricted to few layers and discontinuous? What is the answer? If entire packet of layers, they are folded regionally, then is it possible to have these local, restricted and discontinuous structures, or rather it would be homogeneously distributed continuous structures? What is the answer? Any guess? Okay, so the answer is definitely not. So in case of tectonic deformation, the structures are homogeneously distributed, continuous, and not restricted to single layer. Okay. So for tectonic structures, the deformation would be observed throughout the layers. Yes, there can be heterogeneity within the layers, and that is why you guys have must seen the cleavage refraction kind of things have occurred, because the primary difference in the strength of the material, whether it is a hard rock or is it a soft rock, that would differentiate between the amount of deformation accommodated by each layer or the amount of strain accommodated by each layer. But nevertheless, all the layers would be deformed. So talking in terms of deformation, that would be homogeneous and distributed all over the layers. So the answer for this case, whether it is an overturn crossbedding or a fold, then simply the judgment would be we have to look up, down, above, and beyond that particular structure in the field to observe whether there are similarities in the layers above and below of that sequence. And if we find that there are no such structures in the previous or the uh, forthcoming layer, sorry, not forthcoming, I mean the layer deposited after that or layer deposited before that, if we see that there are no discrepancies in the structure, they all look same, then it is a possible cause of tectonic deformation, because tectonic structures are homogeneous and they should be present in all the layers. Whereas if we see that these kind of folded like structures, they are only restricted to one layer, two layer, and not more than that, and even if they are also restricted within these layers, there are differences in their pattern, right? Some would be much tighter, some would be much shell, I mean widespread, right? There can be internal complexities as well. So if we see these kind of variations within the layers as well, then it definitely tells us that these are not tectonic signatures and they are definitely syn sedimentary deformations, right? So for just to identify whether this is a tectonic structure or this is a syn sedimentary structure, we just need to observe in the field up, down, above and beyond the structure. If we see these are continuous, then possibly it is a tectonic event, and if we see these are discontinuous and local occurrences, then most surely these are syn sedimentary structures. And also the thing is that tectonic structures can occur in any kind of rock, whether it is sedimentary, whether it is igneous or metamorphic rock. Tectonic structures can be I mean, observed in all kinds of rocks, but these cross beddings or convolutes, these kind of structures are essentially restricted to syn sedimentary deformation. Okay, so this is the first point we discussed. So any doubt, any question that you would like to ask? Okay, so coming to our next point, which is secondary structures, I'm sorry, the formation and evolution of simple to complex sedimentary structure, their use of determining the Younging direction and strain markers. So First is determining the Younging direction. So how we determine the Younging direction? So there are different parts. Say for example, cross stratification. There is a geometry known as asymptotic bottom, and the upper part is truncated top. So from asymptotic bottom to truncated top, this is the Younging direction, right? So using this information, how can we utilize this to understand whether a sequence is inverted or not? Anyone? Any guess? So if you observe a overturned fold, how would you identify in the outcrop scale that whether this sequence is overturned or not? And that is simply by observing the Younging direction. So if you find a sequence like this, mm, like this, then this should be the Younging direction. Then the entire sequence is inverted, right? And that is how we can use this stratigraphic Younging direction to estimate the uh, whether the sequence is structurally overturned or inverted, right? Now what is the can anyone say the definitions of antiform, synform, anticline and syncline? Anyone? you guys should interact, because these are not exams or something like that. It's just a course, and it is for your benefit that we should have discussions, so that you can clear your concepts, and that would ultimately help you, right? So uh, please feel free to have discussions, even though this the answer is wrong. Nothing to be ashamed of, because ultimately it is your goal to clarify your doubts, right? So feel free to join the discussion and have interactions. And it is also possible that I am saying something not up to the logic, and you should correct me. But anyway, you should always interact, so that we can have this class in a more well decorated way. So what are the definitions commonly? These are the some common terms that we associate with folds, right? So what is an antiform?
Antiform means a convex upward fold, upward fold formation,
Exactly, very good.
and synform means a convex downward formation of a fold.
Very good, very good.
And
Okay. And okay, so Rohit has clarified these terms very beautifully. So you have to figure out, or you should understand that antiform and anti synform, these two terms, these are geometric terms, right? And anticline and syncline, these are stratigraphic terms. Okay, how so? So first talk about the geometric terms. So geometrically, if a fold is convex upward, okay, so if this is the structure, convex up, this is antiform. And similarly, if we have a convex down or concave up structure, then this is synform, right? But this has nothing to do with the age of the rocks or the age of the sediments, whatever it is. Now, coming to geometric terms, sorry, stratigraphic terms. So, if it is like that, uh, no, let us not draw like this. Instead, Let us represent it like this, right? So this is the center layer, right? So while going from center to the outward, if we see, from center layer to outer layer, younger rocks, then it is called as anticline. Okay, and if we see that, this is the central layer, a center layer going outward. If you see older layers, then it is called syncline, right? Sorry. So it is called syncline. Okay. So anticline and syncline, it has nothing to do with the geometry of the rock. It is just a stratigraphic terminology that whether in a fold from center to outward, whether we are observing sequentially older layers or whether we are observing sequentially younger layers, that defines our terms, whether it is a syncline or anticline, right? Now let us think about it like this, that what would happen for antiformal anticline. So I can mix these four terms: antiformal syncline, synformal syncline, and synformal anticline. These are the four possible type of folds. So for antiformal anticline, what would happen? Say there are three layers, right? L1, L2, and L3. Okay. So the form of the fold is convex up. So convex up means it tells us it is antiformal, right? The form of the fold is convex up. And if I say, if we observe that L1 is older than, sorry, it is older than L2 and older than L3, which means that L1 has highest, L1 is oldest, sorry, and L3 is youngest. So according to our definition, from center to the outer layers, we are seeing that the age is sequentially decreasing. That means the older layers are in the center, and from in the outer layers they are much younger, and therefore this is an anticline, right? Similarly, for antiformal syncline, what would happen if L2, sorry, L1 is less than L2, is less than L3, which means L1 is the youngest and this is the oldest. Then it would be a syncline. Then this would define antiformal syncline, right? Similarly, for synformal syncline, what would happen? So for synformal syncline, so this is L1, this is L2, and this is L3. So this entire structure is convex down. So for synformal syncline, L1 is less than L2, which is less than L3, right? This is syncline, and if L1 is greater than L2 is greater than L3, then it is anticline. So normally these two are normal sequence, right? But these two are inverted sequence. These are inverted sequence. So therefore, the importance of having these kind of inverted sedimentary structures, where you should find the asymptotic bottom at the top and the truncated top at the bottom, it is only possible when you are observing whether a antiformal syncline or synformal anticline, right? Sorry, I wrote wrongly. Let me correct it. Sorry. So these two are actually not the correct sequence. So this one and this one, they are normal. So antiformal anticline and synformal syncline are normal sequences, whereas antiformal syncline and synformal anticline are inverted sequence. Right. So if I ask you that in which of these following cases you would likely to have these inverted cross bedding structures, then what would be the answer?
Anti-formal syncline and synformal anticline.
Exactly. So antiformal syncline or synformal anticline, since these are the inverted sequences, then therefore we should expect to have these inverted sequences, truncated top at the bottom and asymptotic bottom at the top. These kind of structures can we can observe there, right? So this is the importance of this utility. And even for I mean, there are also other markers like convolute. So in case of convolute, we see that they form like this, right? So convex down is, this is the bottom side and this is the top side. This is the water interface during the formation. Sorry, this is the sediment water interface. Sorry. And this is the bottom part. This is, sorry, this is the bottom part. This is the top part. And therefore we have Younging direction like this. Okay. Similarly, if we observe that these convolutes are inverted, then we can say that surely with it could fall under this antiformal syncline and synformal anticline. And antiformal syncline and synformal anticline. So if I conclude this, that they are often associated with overturned folds, because only then we can have this inverted sequence of anticline and syncline. Okay, so this is the utility, I mean, for determining the Younging direction. Now let's talk about the utility of these thin sedimentary structures the as strain markers. Okay. So they form essentially in spherical shape due to deformation. They become elliptical, right? This is primarily from the lecture. It has also been very elaborately described that how this long axis of this ellipse, the long axis of these ellipses would give us the stretching direction, and from that we can actually have an estimate of how much strain has been accommodated by this convolute or sedimentary structures. Now, it is not only that, right? So imagine that there is a horizon bedding plane with traces of bedding plane, and we have these convolute structures, perfectly spherical, right? So shear deformation after lithification would produce elliptical convolutes, right, like this. So the same horizon, it would just be like this, like that. So this is the shear direction, the shear sense, from where we can estimate the long axis, sorry, and then we can calculate the shear strain, right? So it is possible. So these are basically stretching axis, right? But what if the deformation occurs during lithification? This means that the sediments contains a proportion of water, and they are in semi-solid state, right? Because after lithification only the sediments become rock, that means they are solid. But during lithification, what happens during lithification is that the excess water is being released from the pore spaces. Pore compaction takes place. The framework grains, they are oriented according to the deformation. Then we have this matrix development. Then we have the cementation. Okay, and then eventually the diagenesis process is being completed, and from that we get uh, a solid rock, sedimentary rock. So this entire process is called diagenesis. So diagenetic deformation, right? So these deformation, so this is known as diagenetic deformation. So the sediments contain a proportion of water and they are in semi-solid state, right? So what happens if they're semi-solid? Because they remain in semi-solid state, the orientation of sedimentary structures change, simply as that. So sedimentary deformation, diagenetic deformation would cause something like this. So if you try to draw an axis, you would see that random orientations. Same thing can be also observed in the dish pillar structure, like flame structure. So a complex form of deformation, complex diagenetic deformation would produce randomly oriented sedimentary structures, right? So recall the Dhalbhungar exposure. So you have might have seen, right? In the video, you must have seen the Dhalbhungar exposure. So there were lot of dish and pillar structures, right? And they were all oriented haphazardly. So I was explaining that part, and I told that complex deformations have produced these random orientations. Now this is the complex deformation we essentially talk about, is that uh, this kind of I mean, complex deformation is essentially sin diagenetic deformation, and that would produce these randomly oriented uh, structures. Okay, so this Dhalbhumgar exposure is one of the finest exposure in this eastern region, or Shingbhum shear zone, or Shingbhum craton, where we find these kind of sin diagenetic deposition structures. And there can be also another controlling factor. There can be another controlling factor which we uh, need to recall, is that the facies or environment of depositions. Initial energy fluctuations. So initial energy fluctuations during deposition can also contribute to these random orientations, especially in the tidal flat sequences. So the Dhalbhumgar exposure was essentially a tidal flat exposure, because the sediments were deposited in a high energy condition in the tidal flat environment, or let's say not high energy, it is a periodically changing energy condition. Sometimes it is high, sometimes it is low, sometimes again it is high. So uh, these fluctuations in this energy condition, initial energy conditions during deposition, they are also somewhat responsible for uh, disturbing these orientations of these individual structures, right? So that is an important reason. Now it is not always uh, distinguishable that whether these um, deformations are solely contributed from these tidal flat sequences. I mean, is there any I mean, whether these structures have solely formed because of energy fluctuation during deposition, or they are related to sin diagenetic deformation, it is quite hard to figure out just by observing the field exposures, right? So for that we need to do regional mapping. So while doing regional mapping, we observe that there are no such signatures of other kind of tectonic structures, right? So if the terrain is perfectly flat and the sedimentary rocks are not altered, they remained in their initial composition. So in that case, there could be a possible factor that the energy fluctuations might have produced these kind of randomly oriented sequences of these convolute structures or dish and pillar sin sedimentary structures. But if we find that the sedimentary rock is altered, I mean it has undergone a slight metamorphism, or in the regional scale if we find the presence of a fold or any ductile behavior, then we should think about not only these energy fluctuations but also the contributions from diagenetic deformation that must have produced this kind of structures. Okay, so having said that, let us move to the our discussion. What was the point? Yeah, third point is that to estimate a planar geometry from secondary linear data, statistical significance of the data, right? So the third point is, and the question is, how much data should be collected? Say for example, I have this exposure, and again there is another surface. Okay, so here we have the traces of bedding planes, right? So these are traces of bedding planes. So there is another rock surface like that, where the surface is exposed, and we see a different orientation of the bedding plane, right? So it was taught in that video that you should collect the traces or the linear data from the traces of these bedding planes. So these are, so by collecting or say measuring, not collecting, so by measuring the linear data of the traces of the bedding plane, we can reconstruct the actual orientation of the bedding plane through stereo plot, right? Okay, so it is a quite doable thing. You have also seen in this lecture that we have collected the data. Say this is L1 and this is L2 and this is L3, and then we have plotted in the stereo net, right? And from that we have passed a great circle. So if this is L1, this is L2 and this is L3, this gives us the bedding plane. Now what if we only got two data? Then like this, right? So the plane, it can be like this, or it can also be like this, right? This is a possible, this is a possibility one, and let us say that this is the possibility two. Then how to figure out which one is correct? If there are only 2 points, it is very risky to estimate the actual configuration of the bedding plane just by passing a great circle, because we are matching the geometry, and it can be in both sides, either side, right? Whether it could be dipping in one direction, and it could also dip in the opposite direction as well, right? Because geometry, it is just a geometric interpolation of the data. Then how much data should we acquire or measure to say confidently that our data is accurate enough to give you the actual orientation of the bedding plane? So in this case, if we have two data, the the amount of error is quite high, right? So it is more than 100% the error in this case, because it can either be this one or this one. Not so not 100%, say it is 50% the probability. So the probability is 50%, and therefore the error should be like that. So it is either this one or this one. So in field, how much data should we collect? What do you think? It is, of course, comes from the basic sense that the more the merrier, right? So the more data we have, the more accurate it is. But still there should be at least some threshold value, right? Say for example, I have two data, some other guy have measured 10 data. Of course the measurement from the second guy is much more statistically robust than mine, because uh, he or she has 10 data point, I have 2. But then again, what if there is another one who has 100 data? So then the increasing amount of this data point would increase the, or sorry, decrease the chances of error in estimating the actual data. since we are doing estimation, there is always a possibility of error. Then who decides? So this should be the minimum requirement to gain an actual error free or less errored data. So in that case, we apply the concept of central limit theorem in statistics. The central limit theorem of statistics, of the statistical quality of the data. So in short, this theorem tells us that if the sample size or the data cluster has at least 30 points, 30 data points, or individual elements, then together they produce a normal distribution of, or say, a normal distribution. So what is a normal distribution? You must have followed your sedimentary class, sedimentary geology class. So if this is the frequency and this is the class or categories in which we divide the data, so the plot would look like this. So this is known as a bell curve or a Gaussian curve, right? And what is the significance of this kind of curve? So if this is the average value, it is denoted through mu, of course. So if this is the average value, then mean, mu or average, is equal to the median of the data, and it is equal to the mode as well, mode of the distribution. So together this is the characteristics of a normal distribution. And since the mean, the median, and the mode of this kind of distribution is only the single point, I mean, same value is the mode, the median, as the mean as well. So therefore these kind of data would have less error. Okay, sorry, this kind of data would have less error. So in order to follow the central limit theorem, if it is possible, then we should collect at least 30 data points, and we should then examine whether there is, I mean, the error, whether it is decreasing or it is remaining the same at least. So it is said, or it is a standard, that if we at least collect 30 data points, then it is possible to reduce the error within the limits, right? And therefore we can use that data because it is statistically significant. Otherwise, if you have two data, it is statistically not significant. So in while doing field work, you should always consider this thing, that how much data should you should collect, because apart from observing the field, I mean structures, and having interpreting their geometries, it is good enough, but you should also focus behind the quality of data, right? How much data have you collected? So the more the merrier. It is the basic concept we know, but at least you should be encouraged to collect 30 data points for a specific uh, measurement. Now if there is no exposure, then it is not possible every time, but still if there are exposures in that area, go for them and try to collect as much as possible data. Otherwise, just two data points, of course it would give an estimation, at least you can have a hunch that okay, so this can be the orientation of the bedding plane or the foliation, etc. But then you should also focus on st- having a good number of data. So keep in mind that just going to the field and collecting one measurement, whether it is an attitude like strike, deep, anything, pitch, plunge, trend, whatever it is, just not restrict yourself in collecting one or two data. It is it is scientifically not ideal practice. So if you are doing a project, or you are doing a thesis, or any kind of geological mapping, have more number of data. And also it is important that you should not collect data in a cluster, I mean a very single spot. You're sitting in a single spot or a tiny exposure, and you're measuring repeatedly, right? So that is not feasible, right? You have every time you measure a single uh, point, there would be some variation, right? But that won't give you the spatial distribution of the data from which we can actually interpret or sorry, extrapolate the information that you are looking for. So it is necessary that you should also collect data from different locations as well. So this would give you a spatial distribution of data from which you can infer that, so this is the actual orientation, right? So now coming to the last part of our discussion. So in the fourth part, i'm I'm assuming that you have gone through the different relationship between folds and the cleavage, refraction, the foliation bedding interactions, the origin of intersecting lineation or striping lineation, from that the measuring the fold axis, these kind of things you must have gone through. uh, Please kindly mute yourself, whoever is unmuted. Yeah, thank you. So now my question is, this is a significant question. We have measured the different structural data. We measured foliation, lineation, right? We measured deep, strike, pitch, plunge, trend, every possible set of data we have measured. Now from that, So say for example this is a bedding plane, and this is the metamorphic unit, metamorphosed schist, and it is also here. And you have seen cleavage refraction, right? Now these are intersecting lineations, and from the there by measuring these lineations, by measuring the traces of lineation, sorry, foliation, we get a linear data, right? My question is, why are we considering this linear data as a fold axis, even though we did not see the fold, entire fold in the field? So this linear data, so this linear data, it could be anything, any sort of deformation signature. Why specifically fold? Can anyone answer this, or at least think about this? Because it was not discussed in the in this video, right? And I got this opportunity to extend this discussion further because the lectures have their own constraint of time and all these things. But in this discussion session, we surely can discuss about why, even though this structural data could be anything, then why are we calling it as a fold? We didn't say a fold altogether when we were doing or conducting the field. After the entire mapping, we have plotted the limbs, right? But we didn't see the fold, at least in the outcrop scale. Then how could we confirm that these linear data are of a fold, specifically considering this as a fold axis? Any guess, anyone? Anyone? Just a guess. That I hope that you have understood the question, right? Why we are calling it a fold and nothing else? I mean, it could be a fault, right? Why not a fault? Why a fold? Anyone? Any answer? Any guess? Anything? It's fine to have a wrong guess. That's nothing to be worried about. But you should try, because this is this question should come to your mind as well, right? Why are we even considering these entire structures as fold? Nothing. Why not anything else? Okay. So since we are close to our finishing time, let me explain. So this is a rock. Consider this as a rock, right? So if we fold, in what condition could we fold the rock? there should be a specific condition, right? There should be a specific pressure and there should be a specific temperature. Without those things, we cannot actually deform a rock. So to deform a rock or to deform any unit, we need to apply certain pressure and temperature. And at that certain temperature and pressure, this entire material ductile, behaves as a ductile material. The rock becomes ductile. That means it flows. There is a flow nature occurs within the rock. And not just, I mean, this ductility, it just not comes from the rheological changes of the rock, but as well as the uh, compositional variation. So the initial rock that we have observed in the field was a that is a peletic rock. That means it is a sedimentary unit, and then it has undergone a certain metamorphism under green schist facies, and that is why we have seen that there are a lot of mica schists present in that particular area. Now, the presence of mica schist tells us that the host rock must have undergone a condition where it was in an elevated pressure and temperature condition. That means the rock unit became soft. And whenever we apply tectonic forces in a soft rock or a soft material, it has to buckle, right? So imagine if this notepad, if it wasn't soft, if it was a stiff material, then by compression it would simply break, right? Because of this, the brittle nature of the fragile nature of the material, because it is stiffer, then it would break. But it is buckling, that means it is softer and it can accommodate the strain through buckling. So unless and until the material can accommodate the strain through buckling, it would deform through brittle deformation. But if there is an option to accommodate the strain without any kind of development of fracture or loss of cohesion, then the deformation should essentially be propagated through ductile behavior or ductile deformation. And the prominent structures which are formed because of ductile deformation is a fold. And therefore, since we are observing this foliation, this crenulation, the formation of these mineral lineations, intersection lineations, all these things together, and the metamorphosed rock as well, it tells us that the rock must have undergone certain ductile deformation. And since there is an evidence of ductile deformation through these lineation and foliation, I mean linear and planar fabrics, that tells us that the rock must have undergone ductile deformation, and the most prominent ductile deformation signature is fold. That is why we expect the large scale structure to be a fold, because in the large scale or regional scale, the material or the metamorphosed rock must have experienced a certain pressure and temperature that made it soft, and soft rocks would of course fold, not break. And that is why, while talking about all these things together, plotting the stereo nets, mapping, etc., we eventually say, because at the back of our mind we eventually think that okay, so since it is a metamorphosed rock, then the structure has to be a fold. And that is why, even though we didn't see the fold itself in the field, we assume, or we know rather, we know confidently that this has to be a fold. So therefore, by for concluding, we can just simply say the remarks is that by looking into the metamorphosed rocks and the planar and linear fabric, we consider, or we conclude that the regional structure has to be a fold, because fold is a signature of ductile deformation, right? So this is why we are interpreting the entire structure as a fold, and then eventually we see this cleavage refraction, the limbs at the hinge, and cleavage fanning, all these sorts of things in the field. Okay, so I think that it is enough for today's discussion. So if anybody has any question, then please can ask. We can have another few minutes for discussion, then we can conclude this session.
Sir, then it means that the fold axis in the regional fold is determined by, sir,
Yeah, please finish what you are trying to say.
sir, it is by plotting the lineation or by plotting the foliation, sir.
So the availability of the data would tell us that how you are going to proceed. Say for example, in an exposure you found the bedding planes. Okay, so you can plot them by having the planar data. But in case you couldn't find a proper bedding surface exposed, then what should you do? You just only saw the traces of the bedding planes. Then you measure the linear data, and from that you interpret the position of the fold axis or the trend and plunge of the fold axis. So depending on the availability of data, you can plot different things. If you have the data for the bedding planes, then you can mark the limb of the lamb, or limb of the fold in the map. But you have gone to a field in such a location that there are no such exposed bedding planes in the outcrops. Then what would you do? So in that case, if you get these linear data or the traces of the bedding planes, right? So just like in the or the traces of the foliation planes on the bedding plane, anything. So in that case, you measure the linear data, and since from the concepts of your structural geology, you know that so this thing has to be the fold axis, then certainly you can map, I mean plot the fold axis in your geological map to point out so this is the fold axis orientation. And therefore by having sequential orientations of the fold axis, you can actually map where the fold is turning and whether there is any polyphase deformation, right? Or superposed deformation or not. So these kind of things can be concluded. Having the bedding plane data, you can see, you can map the actual morphology of the fold, where the hinge is, where the limbs are, whether there are double hinges or multiple hinges, whether there is a single hinge. These kind of things are possible to be interpreted from the planar data. And from the linear data, it is possible to have uh, a visual evidence whether the fold is turning, or the fold is further deforming, or there are multiple sets of fold axes that would tell us there are different phases of deformation, right? So planar and linear data, they are both useful in different ways. Whereas planar data mostly tells us about the geometric disposition of the feature we are trying to observe. The linear data, they are helpful for us to tell that how many phases of deformation have occurred and whether the deformation has changed in spatially in the map. Okay.
Okay, thank you, sir.
Okay, so if there are no questions, I should conclude this meeting, and then we will have another set of discussion next week. Thank you.